Okay, it's the top of the hour, so let's get started. Welcome everyone. Good day. I'm János Farkas and co-chair the .NET Working Group with Lou Berger. Unfortunately, Lou couldn't make it this time, so I will be the one leading this meeting. I'm affiliated with Ericsson, and we have our secretary, Eve Schuler. Many thanks to Eve for doing a great job. Since you have found your way here, you figured the logistics part of the meeting. I would like to remind everyone of the IETF Note well. These are the rules and policies under which we conduct our activities in the IETF. Please check the details, like there are a lot of references here. If you are not familiar with them, I would like to draw specific attention to the part that all the contributions, that is all what you say here, for example, become part of our permanent records. And by participating, you acknowledge this. I would also like to remind everyone, I mean, the group is great. Just to mention that remind you of our conduct guidelines. So please behave respectful and professional to others. Please mute yourself when you are not speaking, and headsets are recommended. Like we are, I guess, all familiar with the virtual meetings by now. And as I mentioned, I suppose everybody is familiar with the logistics since you have found your ways here, but I would like to remind everyone that note-taking is a joint effort in these meetings. And let me give the link to the chat window. So please join the joint note-taking. You can find the link in the chat as well. Otherwise, the usual places for the meeting materials and so on. And a few words about the agenda. We have a Norm giving us a presentation on ongoing work and developments in the IT Plato 2.1 TSN task group about projects that I think the most relevant to our work in the .NET Working Group. That's the main subject of this interim today. And we will have some time for discussion. I think I would say verbally also what we said before, that at the last IETF, originally we planned this meeting also to start discussion about taxonomy aspects for the enhanced data plane proposals, and the offline preparations did not go as we expected by this time, so we need to reschedule that part of our next steps to another meeting. That's not a subject of the meeting today. Any comments on the agenda? I have one more slide to say, but Thorles, yes, please go ahead.
Yeah, just a quick question on that thing that had to be dropped from the agenda. Would be nice to see discussions about that on the mailing list, what the next steps are, so that we don't have surprises like this one. Only surprises if we're not getting active on the mailing list, right? So that's fine.
Yes, understood. We are continuing offline discussions actually on like how to have an effective meeting so that we are prepared, or there are some preparations ahead that we can meaningfully discuss. That's what I meant actually. And now we are facing the holidays. Honestly, many people start vacation next week, like myself, and come back like 8th of January or so. So please don't expect anything radical in that time frame, but hopefully something in January. You may also remember that we discussed another potentially interim on like the third week of January. I think that was at the time was about the raw aspects, but if we cannot progress that much with the raw architecture, yes, we need to craft plans on how to make next steps with the taxonomy.
Yeah, and remember, right? So I mean, end of February is the big Chinese holiday. Then again, right? So it's always for us from the West. Kind of we easily forget about that. No, I mean, I think the primary thing that I wanted to bring up, which would be good to maybe discuss, is that it's not only about selecting specific mechanisms, but to think about also broader topics resulting from what we've been looking into, like, you know, what extensions to the overall DetNet architecture do we actually want to have for large-scale networks? I think those are questions easier answered with less, I think, contention than the individual mechanism selection based on the work that we've done with the requirements document.
Sure, yes. And again, I think also the one reason for not being able to be well prepared for this meeting is already the holidays. Like many people, some people have started vacation earlier, and we are now facing that everybody is busy for wrapping up the year. Okay, moving on a bit, and then we have some time at the end for discussion. One more slide on the intro part is that actually we have received 2 liaison statements. We haven't sent any. I would mention the coming in later, the one from ITOT Study Group 13 about their efforts on deterministic networking. There are the links here, and you can check the details. Both liaison statements are for information. And I would like to mention the one from 802.1, which is actually about their most relevant projects. And this is what Norm will be presenting, these 2 projects. And many thanks for Norm accepting the invitation and willing to present. And with that, I would switch to Norm's presentation. I have changed the slide deck, and let me give
okay.
Somehow I got a strange message. I'm trying to press the control. Anyway, if you don't get it, you can just tell me when to flip.
Okay. Well, I'll start talking and you can work on giving me control. If anyone has any questions, please speak up. I think most of you know me. I'm funded by Huawei Technologies. I was in DetNet for, at the beginning, I actually applied for the Birds of a Feather session that started DetNet. And I started the architecture draft. I've been working in 802.1 mostly for a very long time. And right now I'm the editor of 2 documents that I think I'm hoping are of relevance to DetNet. Now, first of all, these are the opinions of the author. This has not been approved by IEEE 802.1 or for that matter by Huawei. So this is what I think is going on in 802. There we are. So there are 2 works in progress in the time-sensitive networking task group of 802.1, of which Janos is the chair. And one is Project 802.1 DC, Quality of Service Provision by Network Systems. And the other is the 802.1 QDV, Enhancements to Cyclic Queuing and Forwarding. Now, the first one is in Standards Association ballot, which is the very last ballot and comment cycle before publication. And what this, I'll be talking about this one first, and it allows a system that's not abridged to claim conformance to all of the TSN quality of service standards. And I'll get into what those are. along with Yang modules to support them. So as QoS wise, you can do anything a bridge does without being a bridge and caring about MAC addresses, and certainly not forwarding based on MAC addresses. The other document is QDV. This is an amendment to the 802.1q bridge standard, and it adds a new queuing mechanism, transmission selection mechanism to 802.1q, which is a new form of cyclic queuing and forwarding. We'll talk about what that is. This one is in task group ballot, which is the very first part of the process. So this work is just starting. It's had a lot of presentations on what it is and why it's helpful, but it's just starting the standardization effort. And it provides, as you can read, multi-level nested transmission cycles with output bins selected according to either time of arrival, per flow byte count, or potentially a field in the frame. So let's start with quality of service provision by network systems, 802.1 DC. In our terminology, those capital letters mean this is a standalone document. It's not an addendum or an amendment to 802.1q bridging. It's a document that stands all on its own. There is a big list of features for right now that are defined for bridges in 802.1q. You have run across them, but basically you've got strict priority, weighted fair queuing, per priority credit-based shaper. You've got scheduled output, where you can schedule each of your queues, and you're on for this time. You 3 queues are on, you can fight it out during this time period. This queue is closed at that time period, and so on. We have the primitive form of cyclic queuing and forwarding, which is the whole network advances all the TSN traffic 1 hop per clock tick, all at the same time. That's the original CQF. We've got the newer asynchronous traffic shaping, which is a time-based shaper, which is fully analyzed and gives you full TSN capabilities at some cost in computation. And potentially this new one that we've started working on, QDV, the enhanced CQF. There are a lot of related mechanisms. We've got token bucket yellow, red, green marking. We've got VLAN tagging that you know about with 8 levels of priority and a 2-level green, yellow drop eligibility tag on the frames. We've got priority control, which is better than X on, X off. It's a similar idea, but it's a little better, a little gentler than that. It's mainly to be used at very low level to prevent input buffer overflow. We've got the frame replication and elimination for reliability. You know this. This is in the DetNet architecture document. We've got the per stream filtering and policing, which involves, that can include timed input gates scheduled when certain flows are allowed to come in on this port and when those flows are not allowed to come in this port at other times. Frame filtering and flow identification for QoS purposes. And we know, but you know about frame preemption, where you can interrupt a frame and transmit more time critical transmissions. Now, all of those are included in the feature list of .1 DC. And I want to stress that more important than that list of features is the fact that .1q integrates all these into a structure that defines the interactions among all of these things. And of course, they have strong interactions. In a sense, any standard is a definition that relates managed objects, control parameters, with observed behavior. And it does that via a model. It's got the model, it's got the managed objects, and it can produce the behavior. It produces predictable behavior for anything that conforms to the standard. So any combination of all of those things can be configured, and the result is well defined. You've got the Yang modules. And in particular, frame preemption is integrated into the mix. And TSN time-critical streams can be preempted by even more time-critical streams. That's all part of the model. Now, we all know this feature set is implemented on devices that are not just 802.1q bridges, and people implement them on devices that have no bridge capability at all, of course, because they're ubiquitous. They're in the chips. Now, many of them are. So it's interesting to see that none of these QoS features in .1q actually require that forwarding frames based on MAC addresses is present at all. And to my delight, when I started working on this project, I found that the QoS features are rather well isolated from the rest of the document, that the bridgey stuff and the protocol-y stuff are really separated from the QoS stuff in the text. So we decided to start work on DC to make all of the QoS features referenceable by standards that define hosts or routers or firewalls or load sharing appliances or security appliances or Taka-RAT switches or NICs or any other kind of device that wants to do these kinds of QoS functions, has a path now to specify how to do that. This is the last slide on DC. What is in DC? There's a guidebook to point the reader to the parts of .1q and other documents. There are a number of documents that make up .1q, amendments and so on, and there are also related documents that are relevant. So there's a guidebook, a reader's guide, if you will. There is a list of all the TSN features and a trail of requirements for each feature saying this is exactly what part of .1q you have to pay attention to know what this feature comprises and to be able to implement it and say that you are conformant. And it's got the Yang modules that you need so that you can control these features and you don't have to import spanning tree state or any of that kind of stuff into your device because it's not needed for QoS. So that is .1q. I've got a pointer slide at the end that says where you can look at, where you can see this document if you want to see it. It is in its final stages. Any questions about .1DC?
Florian, please go ahead.
Yeah, thanks. So yeah, thanks a lot for this. I think it's really great to have this opportunity to apply these QoS features to routers and not, I mean, in the past I always tried, okay, this is some kind of a bridge, but it was really hacky. So it's really great to have this. So I actually tried to apply this DC Yang model for .NET router configuration and ran into two minor issues with that. And the first one was that I was not able to find a way to actually configure the priority to traffic class table. And the other thing was, it was not completely clear to me how to really apply the stream identification before the flow classification and metering. Can you comment on that, or should we rather discuss these details offline?
Well, I can give you a very brief thing. The configuring priority mapping, I considered a bridge feature as opposed to a router feature.
Okay.
Okay. So priority mapping, mapping the priority implies it has a priority, a layer 2 priority when it comes in, and you're putting a layer 2 priority when it goes out. And I think technically speaking, that's just not true for a router. It doesn't really, it's not a router's job to carry layer 2 priority through. But
yeah,
so that would be my answer to the first part.
Yeah,
go ahead.
I actually agree with the argument. The problem that I had is, for example, the PSFP also outputs these internal priority values. So I have the problem to map them then to the actual queues.
Yes. Again, how you map things like DSCP to a queue, that would be that has to be in the router spec.
Okay.
Right, from my point of view right now. And the other question was about
the stream identification.
Oh, the stream identification. Stream identification is in another document. That's in 802.1 CB.
Yes. The question was just because I think I have I think I implemented the way it is supposed to be, but it was just a little bit confusing because there is a diagram in the DC document where basically you have the reception port and then directly the flow classification, and I was just expecting some identification in between.
Yes, I've seen that there's a comment on that in the ballot. I ask you to watch the ballot resolution on DC.
Okay. Perfect.
And we'll get into that. Yes. That's confused many people in the past. It will continue to confuse people in the future. There is an answer, and I hope to clarify that better. I hope that a comment on DC will get some text into DC to clarify that. Thank you.
Okay, thanks a lot.
Thank you.
Thank you. Turles.
Yes.
So how would you, I mean, it would be interesting to see an example how, a DetNet flow classification in a Yang model would be brought together with any of the TSN DC actions that should happen for that flow, right? So I can't quite well imagine that.
Well, it's actually in DC.
So there are explicit references to IETF DetNet Yang models?
No. It's to the CB Yang modules, the .1 CB Yang modules.
Remind me, which one is CB?
CB is the frame replication and elimination, which includes flow identification.
Would it be fair to say that it's not quite clear to me now, what the actual proof would be, whether what you folks are doing in DC is sufficient to actually achieve the goal that you have in a context of a router, a DetNet router.
It's not a router spec.
Right.
DC is not a router spec.
But it seems
that's why
that
we're
if it's
talking
not
here. That's why I'm
right.
presenting.
No, but if it's not meant to be able to work in conjunction with already defined DetNet, Yang models to actually establish TSN functions for a DetNet router, then the question is where and how should the missing bits be done? And if the missing bits figure out that there are issues in DC, how would that work? So
that's why
process,
why I'm presenting this, to encourage people to talk about exactly that. I don't have the answers. We didn't do this project in order to meet a specific DetNet need. We got this to separate out the QoS insofar as we define it. But let me give an example. It would be nice to have a token bucket shaper integrated into this model, because in fact people implement a lot of token bucket shapers, and it would be nice to have a token bucket shaper in this model. .1q doesn't have a token bucket shaper. It's got a token bucket red, green, yellow marker, but it doesn't have a token bucket shaper. If DetNet needs a token bucket shaper, let's talk about that, how we can do that, and make a model that works for everything, okay? It takes interest on both sides to cooperate to make that sort of thing happen. And so this is a step in that direction, I hope.
So, as I said, I'm currently working to try to integrate the DetNet Yang, or have some very simple example of using the DetNet Yang model together with DC. I will share it to the mailing list, and then we can maybe discuss about it.
Good, thank you. So we ready then?
Yes, please go on, Norm.
Okay, so TSN where it stands now doesn't scale to large networks. And the two most common issues are that adding or removing a single flow can require recomputing all the parameters for all the flows in the network that you've gotten so far. And that sort of computation load is not ideal for a big, huge network. Also, adding or removing a new flow can require configuring parameters or a state machine in every relay node along the path. So QDV offers, this amendment offers a basis for a variety of related queuing strategies that can reduce these issues, particularly the recomputation of all the parameters. So I'm going to talk about three aspects of this. The basic idea is that you've got several queues. Each queue is divided into bins, and each queue outputs its bins in rotation, or makes its bins eligible for transmission in rotation at a regular frequency, but each queue is at a different frequency. So in that context, we'll talk about the buffer allocation and output timing and so on, the things you see there on the read. And then there's the input side, which is how do you assign received frames, that says receive queues, how do you assign received frames to bins? And we have three methods to talk about: time of arrival, per flow byte counters, and frames marked with a bin number. And we'll talk about scaling trade-offs and time synchronization options and so on, and then some consequences of all this. So I'm going to use this diagram for several slides, as a basis for several slides. And I want to point out, it's not in the text of the slides, but I want to point out this is drawn as the queues that are feeding a physical port. This could just as easily be queues feeding the an aggregated flow. These could be aggregating flows at different QoS levels into a single aggregate flow. This can be merging data in several different QoS levels into a single physical link. Obviously, if you're merging this stuff into an aggregate flow, you wouldn't be having any best effort traffic down there. It would be just the red boxes, just the CQF stuff would be merging into an aggregate flow. But this principle applies hierarchically. Whether you're talking a physical port is just an instance of another kind of aggregate flow. So in this example, I've got 3 CQF queues, and one of them is rotating at 1 millisecond, one is rotating at 3 milliseconds, one is rotating at 6 milliseconds. The one that rotates the fastest is given the highest priority. All of these queues in the .1 queue model wind up feeding into a simple priority selection. Everything feeds into simple priority. What happens is that queues can feel that they're eligible to present something to priority or not. In this case, we've got all of these things feeding in priority. The short period is the highest priority. The longer periods are lower priority. And of course, all the CQF traffic, all the critical traffic is ahead of any traffic that has unbounded bandwidth. So this shows the queues. This picture shows how you allocate bandwidth. I'm assuming that approximately 10% of your bandwidth is taken up by the priority 7 1 millisecond traffic, 30% by the priority 6 3 millisecond traffic, 30% by the priority 5 6 millisecond traffic. Now, these windows are very close together. You would never configure that in reality, but this is an example, and I can only draw so many boxes on a picture. And of course, this is an extremely loaded network. I'm not sure you're allocating 70% of your bandwidth. What this is bringing out is that allocating 40% of priority 6 allocates 40% of your total bandwidth. And really, when doing your admission control, when deciding what you're allowing to pass through the network, to a first approximation, all you have to do is add up the total bandwidth of the CQF traffic per link and make sure it doesn't exceed your configured limits, which is all done outside the box. Can all be done outside the box. Yeah, there's a limit. You can allocate a higher percentage of a slower cycle than you can a really fast cycle. So it's not quite just that simple, but it can be as simple as I don't care what different levels the different flows are at, how many are at the fast flows, how many are slow flows. It's the total bandwidth. All I have to do is not over allocate my total bandwidth on my link.
Norm, do you want
Yes.
to take questions on the fly? Or
Anytime, yes. You interrupt me.
So is for this multi-priority, is that actually standardization-wise new or new explanatory text? Because it seemed to me as if this was already possible with well, CQF being just a configuration method of the pre-existing TSN components, right? So you had the priority queues.
Yes, except the way CQF is described, you need a separate queue for each bin. So it's not practical to have more than one frequency running.
So you're saying that so what exactly could not have been done? So different frequencies of
Well, if you
cycles.
look at the next slide, this is typical buffer utilization. In this example, the priority 7, I'm using some extra buffers to allow for delay variation on my inputs. The second, the priority 6 is the typical case where you have 3 buffers running. And the third case is because it's nice long time periods, I'm able to synchronize them and just use double buffering. So I minimize the buffering. In this example, in CQF, I would require four separate queues for the blue, 3 for the green, and 2 for the red, which adds up to 9 queues. And I would have to have 9 class of service queues. And I only have 8, and that leaves nothing for best effort.
So you're saying that this enhanced CQF would ask for hardware to have more than these 8 priority queues, so to speak?
No, I'm saying that you have a new way of doing a queue, which is very similar, which is actually essentially the same as the asynchronous, the ATS thing, where when a frame is put into the queue, these 4 packets in this priority 7 queue, these 4 packets are in there, but each is marked with its bin number, and you cannot output the stuff in the second bin until the time comes up for the second bin to be output.
But wait a second, these timed queues already existed. That's how CQF, original CQF, was specified.
No. CQF operates by having a whole queue, a big FIFO queue, that it turns on and off. Okay? And it works by selecting which queue you send a frame to based on not just priority, but also whether you're transmitting from the left one or the right one. So you steal 2 queues. And so in CQF, these 4 packets in the priority 7 would be 4 queues, all at priority 7, which are enabled at different times. And so it doesn't matter what priority they're at, because they're enabled all at different times. All it matters is that they're a higher priority than the green.
Okay, wait a second. Let's stick to the most simple comparison for the hardware implication of old CQF versus new CQF.
Let's not, we'll take too long to explain how CQF works today. Let's just talk about how the enhanced CQF is intended to work in this document. The way it works in this document is, and you can't do this with the existing CQF, we can't go into it now, it'll take too much time. Trust me, you can't do it. You have here 3 queues of the 8 dedicated for CQF. Each queue is divided into bins conceptually. You wouldn't implement it that way exactly. And the bins are eligible for transmission and rotation. So a given bin on this queue, on this the topmost queue, 1 bin is actually transmitting. That would be the rightmost bin. 1 bin is actually transmitting. The next 2 bins are full of data, and the 4th bin from the right would be filling. If you look at the green queues, there's a good example. The rightmost bin is emptying, is about to start emptying. The next bin in is sitting there full of data, waiting for its opportunity. And the 3rd bin is right now being filled up. Okay? And in a moment, this rightmost bin will start transmitting. And when that third bin gets filled up, the next bin will start. And 3 milliseconds after this first bit starts transmitting, 3 milliseconds later, the second bin will transmit. And we'll get to a slide that shows that. So this shows the typical buffer utilization. The fact that this top one has a whole lot of buffers shown does not mean that it has a whole lot of data allocated. It's actually the buffer space is consumed by the slow cycles. This would be the output timing. Now this looks similar diagram, but this is time. What happens is that because it's priority, every time a blue frame, every time the top bin rotates, the top queue rotates its bin, it gets to output its frame. So the blue frame comes out first. The green frame is delayed by it can't transmit when it comes up, when it becomes eligible. All three of these queues become eligible at the same moment. But priority 7, the 1 millisecond frame has priority, so it goes out, followed by frames from the 3 millisecond bin. Those are not exhausted before we come up again to another cycle on the fast bin. So the green gets interrupted while that blue frame comes out. When the green frames have been exhausted, now I can start working on the red frames in their slower bin. The red frames get interrupted by the blue frames. And that continues when I've exhausted the blue and the green and the red frames. I've got nothing left in my CQF stuff. So now the best effort can be transmitted, except the best effort gets interrupted for that blue frame right here. And then we start another cycle of red and green. So that's what the data looks like when it comes out on the wire. If I were implementing this, I would want to look and see how much it would cost me to do something to spread the CQF data out a little and make the best effort transmission opportunities less lumpy. So that's the basic idea of CQF.
Norm, we have a question. We have a question from Shafu. Shafu, please go ahead.
Please.
Hello, thank you, Yanis, and thank you, Norm. I have a simple question for this multi-sig, for instance. It seems that it should combine with frame preemption function, right?
Yes, you can use preemption. Preemption of the best effort traffic allows you to reduce the amount of interference with the CQF traffic. And for that matter, you can preempt lower priority CQF traffic in favor of higher priority CQF traffic. I have a paper that is available. There's a pointer to it at the end of the deck that's on the 802 public website that talks about that specifically.
Okay,
how preemption fits.
Thank you.
So what does that buy you? For one thing, admission control is trivial. You mustn't exceed the bandwidth of any given link or some configured fraction, whatever you think is the maximum you want, a CQF you want to do compared to the best effort traffic. So mission control is terrific. The per flow worst case delay computation is trivial or very near trivial, because the number of buffers used per hop is either the number of bin cycles you spend at each hop is either constant or it varies by 1 depending on how you assign traffic to bins. I think there may be cases where it varies by 2, but we'll talk about those things. And the time per buffer, the time spent per bin, is fixed to some accuracy. Physical link delays changes slowly, and we'll talk about that. So the per flow worst case delay computation is just a matter of adding the per hop delays up. And importantly, adding or deleting a flow does not change the delay of any other flow. That's critical, because if adding a flow changes the timing on other flows, then every time you add a flow, you have to recompute the whole world to make sure you haven't spoiled somebody's day of some existing flow. But of course, that comes at a cost. So unlike a token bucket shaper, or unlike the time-based shaper, the ATS shaper we have in .1, where you can have absolutely any flow with any requirement, and you can bring them all together and get deterministic results no matter how you combine things. The downside of that is the computation gets tough. So what you have to do is have a certain number of traffic classes, each with a characteristic period. Every flow is defined with a characteristic period and a number of bytes it can output during that period. That's its share of the bandwidth. And you can't have an infinite number of those. If you have a flow that matches the priority cycle time, then CQF is as efficient as you're going to get. It averages, you buffer 1 frame. You have 1 frame buffered in every hop along the path. Things move along nice and smoothly. And per hop delay is inversely proportional to your speed, and that is exactly what the physics demands of flows that can interfere arbitrarily. If you have multiple cycle times at multiple priority, that allows you to fit a flow to approximately the right priority level. If you give a flow too high a priority, then you don't use all of your transmission opportunities, but you have good delivery time. When you assign a very slow flow to a very fast cycle time, that's basically wasting a lot of allocable bandwidth, but that allows you to do alarm flows that go zipping through the network really fast, even though they're low bandwidth. And so that's one direction of violating the relationship between bandwidth and delay. If you assign a flow to too slow a time, to too low a priority, then you're buffering multiple frames, multiple packets for that flow in one buffer, which means you're eating up network buffer space to deliver it more slowly. So pick your poison. And that's the downside. It's not infinitely flexible. On the other hand, I'll point out that if you're a service provider, having a fixed repertoire of service choices is not an unfamiliar situation. And we'll get to time synchronization. That's important. Any questions on this slide? I think this is a fairly important slide. We got the point across?
Gino, go ahead.
Yeah.
Yeah, Gino, please.
Okay, thank you. Thank you, Norman. I am Gino Zhang. I think that the very important question here is how to determine the duration of the cycle time. It
Right.
affects it affects the performance, the end-to-end latency bound, and so on.
That's right. How many cycles? I will point out a couple of things. One is that you're going to have a repertoire of cycle times. The fastest cycle times may be available only in the parts of the network that have very high-speed links. The parts of the network that have slower speed links are going to have to use will not be able to use the really fast cycle times because the fast cycle time may be shorter than one packet. So the whole network can have a larger repertoire than any given link. But picking these cycle times is a situation that's really quite familiar to the telephone people. There is nothing in this slide that wasn't invented 50 years ago by the telephone folks. Okay.
Yeah. If I may,
yeah,
if I may continue my question,
please.
So we, as you have said, the ideal cycle time is very small, maybe one frame, one transmission time for a frame, right? But in that case, if there are very many flows, we have to allow that many number of cycles, as many as the flows. Then the whole thing becomes recursive again.
No, what you do is if you have a number of flows, they don't each get their own cycle. Let me go back to this. If you have 5 flows at priority 7, then you have to have room in each cell, in each bin, for the frame, for a frame from each of the 5 flows.
Oh, I see.
Okay.
Oh, so each bin has to accommodate all the flows packets or all the flows frames.
Right. This blue isn't just one frame. The green is not just one frame. It is all of the frames at that priority level.
Okay, thank you. My another question is, so do you assume a bursty traffic? So if a single flow transmit a burst of packets or frames at once, then do you have to accommodate all the bursts in a single bin?
That's handled at the edge, and we'll get to that.
Oh, you mean
you'll... edge. You cannot have a burst. Every one of these cycles, the rules for these cycles are that any given flow has a maximum number of bytes per cycle that's allocated to that flow. It can use it or not. If it doesn't use it, those bytes are available for best effort.
Okay, I see.
They've been allocated and they're gone in terms of allocation.
Yeah, but I think in that is the case. And the source wants to send the bursty traffic, such as the video streaming.
Right.
Then the whole whole burst has to wait at the edge of the network, and that has to be counted as end-to-end latency.
Well, you have alternatives. One alternative is to hold it you're going to allocate some amount of bandwidth for this flow. Okay. One alternative is to allocate something that's slightly larger than the average bandwidth, in which case when a burst comes in, it has to be spread out in time, which, depending on your application, simply may not work. The alternative is to allocate it more bandwidth, allocate it 90% equal to some percentage of the burst rate, in which case the burst has to slow up just a little bit at the edge, which may be acceptable, or allocate it a bandwidth equal to its maximum burst rate, in which case the network, in which case you've used up a lot of your network's available CQF bandwidth, and that's not available for other flows.
I see. Okay.
Okay.
So yeah, because the question becomes too long, I may summarize like this. So we have to have some solutions to come in the future about the bursty traffic. I will think about it myself. Thank you very much. Thank you, Norman.
Okay, please do. I wish you luck.
Okay, thank you.
So,
just one more point. It's less a question, but have you compared the scheduling mechanisms that you described with ATS? Because it seems to me that it's not really all that. I think you've got the same problem in setting up the policies, selecting parameters as in ATS. The big difference is just that the arrival time, the earliest, may be shorter in ATS when you add and remove flows, but the guaranteed one that you have will not change either.
You can argue, and I think it's a valid argument, that if you use a large grain clock to drive your ATS scheduler, that and play some games when you're allocating bandwidth, there is a continuum between ATS and this multi-CQF. Okay, and that's brought out in the draft document.
Well, but I was thinking, even if you don't do that, even if you compare just what percentage of bandwidth do you give to each ATS priority, what the maximum buffer size is you give to them, that ends you up with a very similar comparable questions of policies.
Okay, you have to. If the problem you're trying to solve is is more or less continuous flows that can reasonably be characterized solely by their bandwidth. And if there's no coordination among the transmitters to avoid each other's bursts and so on, the best you can possibly do is that the per hop delay, the per hop forwarding delay, the time to get through each forwarding device, is inversely proportional to your bandwidth, and you're buffering 1 packet per hop. That's just physics. And both ATS and CQF offer that. ATS offers it for all the flows at the expense of having to compute it, which is simply an intractable problem for a large network. CQF does it, is trivial computation, but it's only optimal for flows that exactly match your available classes of service. And it's suboptimal for any flow that doesn't match a class of service. So there's no such thing as a free lunch. Okay, this is another point on the, I think this is at one end of the scale. ATS is at the other end of the scale, but they are fundamentally the same algorithm. Yes.
Well, I was just, I mean, thanks for the detailed insight. I was just thinking that this multi-priority doesn't open up any new policy questions that you didn't have to deal with in multi-priority ATS either.
I'm not sure what you mean by that, but you're a smart guy. I'll believe you. So I want to stress that what's critical with this whole thing is we're talking about, TDM over best effort. Okay, we're talking about phone circuits over best effort. What's critical is that every hop, all of the CQF frames are arranged in a transmission timeline that adheres to these rules, that the bins rotate regularly, that bins at different priorities on the same port are integrally aligned, and that no bin is ever over-allocated, so that every bin is guaranteed to empty before its time expires. That ensures that interference on all levels is bounded and easily calculated. So let's talk about how you fill the bins. Now, I've taken an hour, so I'm going to have to hurry up a little, unless you guys are comfortable. So I'm assuming for a moment we're looking just at one priority level, not a bunch of priority levels. I'm just looking at one of them. The rotation frequencies are approximately the same frequency at every hop along the path, and that the phase of the rotation cycle varies along the path. That means it's not required that all bridges rotate their bins at the same moment. It's not required. We've got three clear, obvious methods for assigning an incoming frame to a particular bin on an output queue. One is based on what bin it was in the previous hop. The basic idea is that for all this to work, you want one technique is for frames that are in the same bin at one hop. If they go to the next hop to the same output port, they'll all be in the same bin. Again, that's what enables you to not have to look at the frames and not have any per flow state machines, no per flow state at all. So you've got to know what bin number the frame was in at the last hop. You can get that from the time of arrival of the frame. That's in .1QDV right now. You could get that from some field in the frame. Now, I know this has been discussed in DetNet and in IETF. It is not in the current QDV draft. And I will just mention to you so that I have an assumption in my head that's somewhat different from the presentations I've seen, and I don't want that to cause confusion. I'm assuming the frame is marked with what bin it was transmitted from. I'm without going into why, I like to think of it as marking what bin the frame was transmitted from, I don't think of the marker as telling me exactly what frame it's going into, if for no other reason than there are multicasts to deal with. So one way to assign it to a bin is I know what bin it came from, therefore I know whether it should go into the same bin as the last frame I passed on or whether it should go into a new one. The other way is to select the bin based on counting bytes, how many bytes I've stored in each output bin per flow. That also works. I invite you to look at this offline.
No,
Yes.
don't worry about time. We have time. We have
Okay.
booked this meeting for 2 hours, so feel free to explain. I think
Okay.
it's a complex figure and it's helpful and it's good discussion. So
Okay.
again, many thanks for doing it. We have time.
So this is two nodes. We've got node A and node B. Node A is transmitting to node B. And I've marked out four timelines here. So the first timeline is transmitting bins. I'm transmitting frames from bin A. The frames in bin A are transmitted between time 0 and time 1. I think time is reversed here from the other diagram. It doesn't matter. You'll figure that out. They're transmitted between time 0 and time 1, and they're received sometime later. I'm assuming 0.3 of a cycle. TC is the cycle time. They're received sometime later. So timeline 2 is when the frames are received, offset, when the first bit of each frame is received, offset by the link delay. It takes a certain amount of time to figure out what I'm going to do with the frame, what port I'm going to forward it to, what kind of QoS. I've got to process the frame. I've got to do something with it somehow. Arbitrarily, I've chosen a fairly long time here, 0.8 ticks. So there is a worst case delay. And by the end of that time, I must have assigned this frame, this incoming frame, to this incoming packet to a bin. So the third timeline is bin assignment time. And this is the critical line that I was talking about in this slide, the timeline paragraph. There must be a schedule, okay, that meets all the criteria, that you never put too much data in a bin. There's always going to be time to empty the bin. Every flow gets its share of the bin. That is enforced at some point, and that is timeline 3, when I'm assigning frames to bins. Having assigned it to a bin, at the moment I close, and this is the end of the time to be able to assign something to bin A, bin C is still transmitting. So at some point after that time, that closing time, I'm no longer able to store stuff into bin A. Bin A then becomes enabled for transmission, and it gets transmitted. So the time from timeline 2, the start of cycle A in timeline 2 to the start of cycle A in timeline 4 is basically the delay across this bridge. Does this diagram make sense to people? So this is the timeline I used if I'm basing my bin selection for this hop on the bin that it was in the previous hop. When the frame arrives, or while I'm forwarding it, I have to identify what bin it was in so that I can apply an offset and assign it to the bin it was transmitted. Now, I will point out that the frames that come in from bin A from node A to node B, those frames go to different ports. So another port may have its timeline 4 in a different phase. Not all my ports may be in phase, although they're operating at the same frequency. So the relationship between timeline 3 and timeline 4 will vary from port to port. And so this gives you a picture of what's going on when I'm trying to keep everything in the bin all the way through. Now, what does that require? The advantage of doing this is that there are no per flow state machines. There are no per flow configuration. The delivery time, end-to-end delivery time, is constant modulo 1 bin rotation cycle. This is as deterministic as things are going to get, and this is the minimum possible penalty when you want to recompute, add a flow. You can't get better than none. So, except for the fact that not all flows are going to exactly fit your available classes of service, and therefore either have to waste bandwidth by going into too high a priority, or, waste allocable bandwidth by going into too high a priority, or waste buffer space by going into too low a priority. It's ideal because it's simple for the network to do, and so that scales. My goodness, that scales. However, it requires, if you're going to keep everything at the same bin all the way through the network, that requires that every single node in the network rotate its bins at exactly the same frequency. What do I mean by exactly the same frequency? That means that if you're operating at a rotation period of 1 millisecond, that you have exactly 86.4 million cycles per day. So meaning that the difference in the number of bin rotations between two boxes, the difference in how many I've counted over an arbitrarily long period of time with the number that you've counted has to be bounded. But this is not a trivial problem, but it's way easier than synchronizing time to a high precision. Okay? If the bins are rotating at 1 millisecond, then it costs you one extra buffer, one extra bin, to have a phase inaccuracy that wanders around over a millisecond range. Okay? If I keep the same frequency, but I get a little off in the absolute, if I get a little off from you, and I wander a little here and there, as long as that wandering is on the order of a bin, then I only need on the order of a bin's extra buffering to accommodate that. And that's a different problem than trying to get sub-nanosecond time synchronization. That makes it, I think, possible to have reasonable sized frequency lock regions. I'm calling them frequency lock regions. I will mention that you do have to track the phase relationship between my bin rotation and the previous hop's bin rotation. If I'm going to do this by timing rather than labeling in the frames, I have to track that to a high precision, but that's a one-way thing. It's a trivial protocol, and it's in the draft. That allows the phase between my bin rotation and your bin rotation to vary slowly, which in fact is what it does. It doesn't jump around. So, for example, if a long link stores 2 cycles of data, and that long link can vary in length over or for that matter, a long link might store a dozen cycles. And if that link can vary by a large fraction of a cycle over the course of a day, that's okay. You need a little bit of extra buffering. You need however much extra buffering corresponds to the time that the link delay can vary. And you can accommodate link delay variation in the same way that you can accommodate limited variations in frequency over a short period of time, as long as at the end of the day, you've added up the same number of buffers so you don't miss a gear, so the gears don't fail to mesh.
Norm, we have questions.
Please.
So,
Yeah, or differences of opinion. So I mean, we've been in the DetNet proposals that we've been having up for since 5 years. The tagged cyclic queuing looked into that as well. So I don't think you can say it's simply frequencies utilization, because you can't have the bins drift apart arbitrarily. You need to have an upper bound, which in PTP fashion is called the maximum time interval. But yeah,
Right.
that maximum time interval can now be in the order of, a few cycles, whereas it had to be, I think, in the clock synchronization in CQF in the order of less than 1% of the cycle time, right? So
Right.
it's,
Exactly.
it's a humongous order of difference, less clock synchronization accuracy needed. The extent to which this results in easier to implement clock synchronization, I think, is still something to evaluate. When I was talking to some of the PTP experts, they were saying that obviously the cost for clock synchronization goes up quite dramatically the closer you get into the nanosecond area. So yeah, I'll be very hopeful that this will be very helpful to further proliferation of this mechanism. That's why we've also been proposing that into DetNet.
Good. I'm hopeful that that's true. I'm glad we're in the same on the same page here. Now, another question.
Yeah, Norman, this is Jin Zhang again. I actually wrote my question in the chat box, so you can take a look. But if I repeat, so you said that the duration of cycle is determined by the number of flows and their packet sizes. So sum of the packet sizes of all the flows, that is the determinant factor of the cycle duration, right? Then
Yeah.
even the highest priority cycle can be very long. You
Well-
want to make it short, but there are a lot of flows of the highest flow. That is the case. And in that case, the low priority cycle, which does not have many flows, that duration becomes unnecessarily larger, I think.
No, I don't think so. The reason is that the reason those flows are in a lower priority is not because they're less important. They're in a lower priority because they have less bandwidth. The high priority are the highest bandwidth. The low priority are the lowest bandwidth. When I say that a flow fits the class of service it's assigned to, you assign a flow to the class of service. Ideally, you assign it so that it gets one packet per cycle. Okay.
I'm not
That's the
sure if
ideal
I
assignment.
understood correctly, but what do you mean by high bandwidth? I don't understand. The high priority traffic has high bandwidth.
How many? Okay, let's talk about it's bytes per second.
But the industrial control packets have only small bandwidth, but has high priority. And video streams can be lower priority, but has more bandwidth, I would say. So it is
Okay.
not.
Okay, we're getting we're getting into the basics, and let's talk about that briefly. If you want to deliver frames, if you want to deliver packets with zero congestion loss, and that's our goal, is zero congestion loss. You don't want to buffer things. You don't want to have things sitting around in buffers. But flows can interfere with each other. You have to have enough buffering to take care of the interfering between flows. If everybody happens to transmit a frame at the same time, you have to be able to deal with it. So if you think of one bin has to be able to accommodate all the data from all the flows that operate at that speed. That way, it's guaranteed you've got enough room if they all transmit at the same time. If you're using the minimum amount of buffering in the network, then it's the case that for every flow, let's assume for a moment that all flows have equal sized frames. Okay, that every frame of a flow is the same size for a moment. That makes thinking about it easier. Then the ideal situation is that every flow has one frame buffered in every node along the path, and that every frame spins one, that the number of frames per second that you're transmitting is equal to the number of hops per second that you get through the network. That ensures that the network will always be able to transmit when it needs to transmit. That ensures that the network never misses an opportunity to transmit. It ensures that all of your allocated bandwidth is available. So your per hop delay is inversely proportional to your packets per second. That's just the law of physics for the kind of flows we're talking about. That's a critical thing that that you need to understand, that the per hop delay is inversely getting through a node. Forget about link delay for a minute. If all link delays are zero, then the per hop delay is inversely proportional to your packet rate. You can't do better than that unless the flows cooperate and stay out of each other's way somehow, which we're assuming they're not. Okay?
Yes, right.
If they're bursty, if they want to transmit more data occasionally, then you have to allocate them more bandwidth.
Right. Yeah, that's the same. Yeah, that's the point.
So
we have we have multiple.
Okay, getting back to your question now. Now that we've established that,
Okay.
getting back to your question. If you've got a whole bunch of of these flows that are high priority, yes, they take up that requires a certain cycle size to match that. That implies you have a whole bunch of flows that have the same bandwidth, and that's fine. And you're right. That means the next level has to be somewhat bigger than that. So you can't have a whole lot of flows that are slower than that, because if you're if your short frame size is just big enough to hold your fast flows, then you've allocated 100% of your bandwidth. So your small bin is going to be considerably larger than the amount of data that it transmits per cycle, because otherwise there's no bandwidth left for any other traffic. And yes, the next larger bin has to be at least twice that size. But okay, if you've got a lot of flows that need that next larger cycle, then okay, you could allocate a bin that's twice that size. It's whatever kind of mix of flows you have. As I said, it's not, your observation is correct. This is not infinitely flexible. You could have 25 classes of service. I'm serious. You could have 25 classes of service, and each class of service has 2 bins compared to the adjacent class of service. Okay, that gives you a great deal of flexibility, and that is possible if that's what you want to do.
Thank you for your kind answer. One way to solve it, I'm not so sure, but we can allocate a flow, a priority, maybe. So according to your hierarchical definition of the classes and the size of the duration of the cycle, we can only allow a small number of flows to the highest priority bins, and we can allow more traffic to become a low priority traffic, and so on. That can be I think that can be a solution.
Well,
or not. I'm not so
maybe
sure.
we'll talk about that at some point.
Okay. Yeah. Let's talk about later.
Okay.
Thank you.
Thank you. So the next big thing is to select based on byte counts. If I'm not frequency locked.
Sorry, Norm. Tong has a comment
Tong,
question.
go ahead.
Sorry, Norm, to interrupt. I just want to join the discussion. I think in your diagram of multiple queues with different priority, I think in this kind of CQF scheme, the priority is for the queues, but not for the flows, because all of the flow has its own latency requirement. So we allocate these flows to different bins.
Thank you.
By the requirement of latency, so the flow priority is not so important in the schedule on each node. So we don't need to mix the priority of queues and the priority of flows in discussion. We need to allocate the flows into different queues. That's what I want to add. And if in my understanding, if some high speed flows or low latency flow, I mean those traffic need to be forwarded in short time. It should be put into the 1 millisecond bins to achieve the lowest latency and also the highest bandwidth. If they don't have a high speed traffic, then some bandwidth are wasted. Yes, that's my understanding of this scheme.
Thank you, Tong. That's exactly right. I agree with you. And that is this slide. The optimal world for the provider is that equipment's used efficiently and so on. These priorities are strictly bandwidth classes. Okay. And you can assign something to a higher priority, and that eats up the bandwidth of a higher, if you want to give it a higher priority, that gives it lower latency, but that eats up the bandwidth of a higher bandwidth flow. Yes. That's bullet 2A or 2B, and that's exactly this. Yes, exactly right. Thank you for making that point.
Okay, thank you.
we can have per flow, per output port, per queue, we can have a byte counting state machine. This is Mick Siemens' Paternoster algorithm, and you can spool the data out into each bin. And I can say that when a frame comes in, I put it in the bin that's closest to the output bin that is not yet full of data from this flow. So each flow can be potentially being assigned to a different bin at different stages, so that I don't care at what rate the data comes in. I assign it to the bins, ensuring that no flow gets more than its share. No flow gets more than its fixed number of bytes per bin. And there are lots of ways that I can use this technique. I can use this as my main mechanism. And I give a little bit of over provisioning proportional to my clock inaccuracies, so that if the previous hop is faster than me, that's okay, because occasionally a bin won't be full and I'll be able to catch up. So basically you don't provision, you don't allocate all of your bandwidth. You reserve some fraction to handle for the clock inaccuracies. That way you can still run as if you were frequency locked and you still get most of the benefits. The catch is you have to have these per port machines to spool out the data. So I can use them by themselves. I can use them at flow ingress or at the boundary between frequency lock regions to recondition the flows and get them back into frequency locked mode. That way I minimize, that way I've got compatible mechanisms all through the network. I just have to count bytes at the boundaries. I can, if I have a place where I have to change the rotation frequency, if I have my bins operating at 1 millisecond and I want to shift to this flow to a thing that's running at 1.67 milliseconds, then I'll have to use the byte counters to make that transition. One method of supporting flow aggregation and disaggregation is to use byte counters. There are other ways to support flow aggregation and disaggregation. And even within a frequency locked region, if I don't trust my neighbors to work properly, I may want to implement the flow counters, the byte counters occasionally at certain places in my network to make sure I haven't screwed up and have somebody somehow with extra bandwidth that they shouldn't have. So I can use the byte counts, the Paternoster algorithm, in a lot of ways. It can be the basis of my network if I don't want to do any kind of frequency locking. I can use it and it's compatible. One thing that's in QD.
No, we have a question from Shafu.
Go ahead.
Shafu, please.
Hi, Norman. Thank you. My question is that if we use account-based bin assignment, then the probable latency may not be same as the time-based bin assignment, right?
Say that again.
My question is that if we use count-based bin assignment, then the performance latency equation maybe not the same as the time-based method.
The which equation?
Yes, the latency, the
Yeah.
performance
Okay. The latency is the latency is a little harder to calculate.
Yes.
And I will refer you to Mick's paper at the end of the. I've got pointers at the end of the paper of this presentation. They point you to Mick's paper. He talks about the latency in more detail.
Okay, thank you.
Okay, there's a paper at the end of this thing. I'll point you to it that talks about that in detail. One thing I'd like to point out is that at each node along a flow's path can use a different number of bins per output queue. And each one can use a different bin selection mechanism. As I go from hop to hop, I can use a label on this hop, I can use time on this hop, I can use a byte counter on this other hop. One output bin can be fed by input ports or even individual flows using any of the three methods. My whole network doesn't have to be time-based. My whole network doesn't have to be label-based or count-based. In fact, I can have on port 6, I can have data coming in on port 1 that's using time to determine which bin in port 6 it goes into. The data coming in on port 2 can use a label to determine which bin in port 6 I'm going to. And a third one can use labels for most of us, but for some flows, I use a counter to determine which bin it goes into. A multicast flow, one input flow, can be sent to different output ports using different bin selection methods. So there's nothing that restricts you in that sense, except the physics and configuring the parameters if you're using a method that configures the parameters. You can use the bin counting even though you're frequency locked. You can use the byte counting, I should say, even though you're frequency locked, if that's what you need to do for safety. Okay, you can use the bin counting to enter a frequency locked region. You can only use time or label to assign a frame if the port to which you're sending the frame is frequency locked to the port that the frame was transmitted from, the last hop. Otherwise, it doesn't make sense. But you can mix and match these things to an arbitrary degree. And one thing that I don't think I mentioned here, you can even assign a frame. You can add an arbitrary additional number of bins to the bin assignment for certain flows, certain ports, or all flows, whatever, so that you can do delay matching. We've run into the issue in a ring, for example, if I'm transmitting both directions on the ring for redundancy, and the exit from the ring is 2 hops to the left and 12 hops to the right. On the short path, I may want to delay all that data for 10 extra hops so that it's delivered, it arrives at the same time, it goes out at matching times to the next ring. So you can actually easily use this scheme to do delay matching and arbitrarily delay flows, obviously at the cost of buffering them. Finally.
Hello, Norma.
Yes.
I have another question. I also wrote it on the chat box. My question is, if you have to count the bytes of flows, then should you maintain the flow state?
What do you mean the flow state?
Well, you have to, I think you have to count the bytes that is already allocated to a bins.
Well, you're counting the bytes that have been allocated. You're counting the bytes that have been placed in the bin for this flow. You have a separate
so
counter for
you
each
have
flow.
to you have to remember some records of flow. Then can we say that's the flow state?
Well, that is a part of that is a kind of flow state. Yes. How many bytes you've put into this bin, and when the bin advances, you know, it clears it.
And,
so,
but
yeah.
you know, the ATS has a problem of maintaining the flow state, and that is the reason it doesn't scale.
Well, of course, that's
so
right.
I think the byte counting CQF has the same problem.
Well, of course it does. Of course it does. That's why.
Okay.
That's why I suggest that while you can use it everywhere, it's best used at the boundaries between frequency lock regions. For example, if you have a region, if you have a boundary where you simply cannot frequency lock, then you have no choice.
But you know, at the network boundary, there can be large number of flows.
Well, ideally, you reduce those flows to a small number of aggregated flows.
Okay. I see. So you try to solve that problem by flow aggregation. Okay.
That's all you can do. That's the physics.
Okay. Thank you.
Okay. It's physics. I can't change that. If you're time locked, you don't have to do that. If you're not time locked, then you've got to count bytes. So you better count bytes on a few aggregated flows rather than thousands of flows. And I should say aggregated. We'll get into flow aggregation. This is my last slide. Flow aggregation. Obviously, flow aggregation is critical, and I've not talked about it very much. I did mention at the beginning that this whole paradigm here is applicable both at a port level and at the entrance to an aggregation. You can be doing this in order to combine flows into an aggregate. And I'm convinced that it's possible. For example, I've got a box. I've got a high-speed aggregate flow coming in from port 1 to port and going out on port 2. I have another high-speed aggregate flow going from port 11 to port 12. I want to separate out one or two component flows from the first aggregate and transfer them and insert them into the second aggregate. I'm convinced I can do that without slowing down either of the aggregates. The aggregate data will still move through quickly. Those flows that I separate out will not move through the box at the same speed as their aggregate that they used to be members of and are joining. They have to find their place in the new aggregate. That takes a bin time. So I'm convinced that there are no unsolvable issues with flow aggregation, that flow aggregation from a QoS standpoint can do what we need done. Now, let's get into some details here and say what details we don't want to get into and what 802 has not done. So obviously flow aggregation is critical. We have not, no one has proposed in 802.1 a multi-layer flow wrapper protocol to wrap flows into an aggregate. No one has proposed one. I'm rather hoping they don't, to be honest, but that's a personal opinion. I will point out that the flow identification methods that we have defined in 802 do support implicit flow aggregation. That is, I can recognize 25 different flows and assign them all the same handle, the same stream handle, we call it, and then I treat them all as belonging to a single flow. So I can do flow aggregation by recognizing all the individual flows and assigning them to an aggregate. And that is sufficient in a small network for obtaining the value of flow aggregation. And the big value of flow aggregation is that after you've aggregated the flows, they go flashing through the network with lower per hop delay. I've got another slide deck that I talk about that. It's publicly available and it's got a lot of wrong stuff in it. So I don't highly recommend it and I didn't point to it in this. But flow aggregation gets you a huge speed advantage. It greatly reduces your end-to-end delay. So flow aggregation is critical for several reasons. One is reducing state, but the other is getting data through faster. Aggregation speed everything, greatly reduce your delay. I want to stress that. And so we can get that in .1 with implicit aggregation. Now, I've mentioned this before. You can use this bin rotation mechanism to aggregate your flows. And I'll say that QDV is a good fit for aggregation because it delivers the aggregated flow at a steady rate. And that's important. If the aggregated flow doesn't move at a steady rate, if it varies in speed, that increases greatly the amount of buffering you need when you disassemble the aggregation. And in a frequency locked region, I believe that in a frequency locked region, you can do flow aggregation, disaggregation, splitting, merging, mixing with the minimum possible number of buffers, meaning that delay at every hop is inversely proportional to bandwidth, okay? And that same for buffer space. So I believe you can, if you're frequency locked, you can do an optimal job. Now, one thing I have not talked about a great deal is labeling the bins. I'll just do this orally. That's the end of the presentation. Bin tagging or marking the frames with bin numbers versus using time. I've convinced myself that a combination of protocol or marking frames or running a protocol separately and timing, locking my input clock to your transmit clock in some fashion are both necessary to make any of this work at all. And you can shift around. You can use primarily labeling, but you have to have some time checks there periodically. You can use primarily time, but you have to have some protocol checks periodically to make the frequency lock system work. When you do aggregation and you go to split out that aggregation, either to pull out one flow to send to another aggregate, or to just terminate the aggregation and split up everything, you've got the same problem at the end of that aggregation that you have from one end of a link to another in terms of identifying which bin the frame came from. And every frame has as many bin IDs as it is deep in an aggregate. So if I've got an aggregate of aggregates of flows, then those inner flows have 3 bin IDs for the outer aggregate, the inner aggregate, and the flow itself. They have 3 characteristic cycle times, 3 bin IDs that have to be identified when that flow gets out to the edge, and has to be in some sense synchronized with where it went into the aggregate or the link that it went into. And I'm convinced there's no trivial answer to that. There's no one answer. I know that at the outermost level, the link level, I can get away with just looking at arrival times of the frames using the .3 timestamp. That doesn't really apply to separating out the components of an aggregate. So I'm convinced that some kind of wrapper protocol or something is required. But there's a lot of room, whether you do that with bin numbers, whether you have time markers, whether you have SONET framing information. There are a lot of ways to do that, but however you do it, I believe that this is the basis for how you do it. That this timeline number 3, assigning everything to a schedule where you meet all the requirements for bins, is the heart of how you do TDM at all. And I think that's the only, TDM is the only thing that scales to a large network. And I think QDV is a good foundation for that. Right now, there's none of the higher level protocols. And I'm pleased about that, because that is where cooperation with IETF is what makes it happen. So, any final questions?
Can I?
Yes, Gino, please. Yes.
Yeah, I have one question. It is not directly related to your presentation today, but the success of the internet was based on the statistical multiplexing and its efficiency. But somehow our TSN and DNet is trying to go back to the TDM era.
Right, telephones.
Yeah. I'm not so sure if that is the right direction. Actually, in that networking group, we are still one way of our focus is based on the statistical multiplexing and work conserving schedulers. I think that is one way of going, and I think that is the right direction.
Well,
yeah. Thank you.
I couldn't agree with you more. Now, so what is happening, what we observe in TSN is that people who have always done things with a big wiring harness and lots of individual copper wires. And I push a button here, and that, at the speed of light, turns on something at the other end. Have gone to special purpose networks, and now they're thinking about, well, the special purpose networks, I have to rethink my PHY every 5 years, and I'm getting tired of that. Why don't I piggyback on Ethernet and let them do the hard job? But they still want it to work as if I push a button and at the speed of light, the current flows at the other end. I think the way you do things is you use different algorithms where you have smarts at both ends, and you have a model, and both ends have the model, and I tell you, I give you frequent updates as to what I want to see happen at your end, and you make that happen. Rather than telling you, right now, put in an extra 0.2 of an amp to the motor. And expect that to stop the train at the right place. But that's a different way of thinking about your problem. You've got engineers that are really good engineers that have figured out their problems, and now they want to translate that problem to an Ethernet network. You can't just tell them you're thinking about your problem the wrong way. Then they don't buy your equipment.
Okay.
So I suspect there are problems. I know there are problems in the small scale where the best way to go about it is to make the network behave more like a push button operating a light bulb. If I look at the service provider thing, when I look at what we're talking about, being able to offer someone a guaranteed bandwidth and say, here's a pipe, I guarantee this is as good as an Ethernet link. You will never lose a frame. You have this much bandwidth and you will never lose a frame due to congestion. Okay? I see that as having some value.
Okay. Norman?
This is the only way I know to do that.
So
Okay,
Gino,
thank you very
I'm
much.
sorry
Yeah.
to interrupt, but actually we have 3 minutes left and
Right,
two more
right,
people
yeah.
in the queue. So maybe we could give some time for them to make their
Okay, yeah.
expression.
Thank you very much, Norman. I want to discuss with you more about this thing later. Thank you.
Okay.
Torles, please go ahead.
Yeah, I wanted to just on this point, I think the model of a deterministic bounded latency just has in the design of many control application a lot of benefits of trying to haggle around with stochastics, right? Because when you're trying to build something reliable and you're using a stochastic model, you're also in a big amount of probabilistic complexities, and I haven't seen anybody who's managed to allow people who want to deploy a reliable, deterministically reliable system to get away from not having to hire math experts on that. Whereas I think when we do have a well-written deterministic bounded latency controller plane system, that you can really deploy that without having to understand complex math.
Well, I feel very strongly that what I've just presented does not require any complex math. It gives you the answer, it supplies what you want, and it doesn't take the sophisticated math. It takes addition.
Okay, Tong Tong, please.
Okay, thank you. I just have want to add a comment that to me, TSN is not only a TDM scheme. It has time-based methods and also asynchronized methods. That's why I think in normal standards there are time-based CQF and counter-based CQF. So either way can have bounded latency, but have different formula maybe. But I think both approach can give us a bounded latency performance. That's just what I want to comment. Thank you.
Thank you. If I can say one last word, why did I give this presentation? The reason I gave this presentation is that I'm hoping DetNet will look at this, the combination of these two documents, assuming this is going to go ahead, assuming this is going to go into .1DC, that DetNet would consider making that as the basis for whatever you're doing in order to scale up. Because I think the physics are going to tell you that the only way to scale up is to do TDM. And I think this is a place to start.
Thank you very much, Norman. Really appreciate it. Many thanks for you allocating the time to give the presentation and make the preparations and join us in this early hour of yours.
Yeah, and thank you for letting me pontificate.
And many thanks for everyone for the good discussion. Time is up. David, if you want to say a few words, please.
I just wanted to echo your remarks, Charles. Charles. Thank you very much, Norm. Very useful. Excellent use of 2 hours.
Indeed.
Great.
Thank you. Thanks, everyone. Let's call it the end. We are adjourned. And keep continuing the discussion on the list on how to proceed. Thank you.
You.
Bye. Happy holidays if we don't talk to you then.